going to record this. Equation number 1, when we're talking about UARM, usually has to do with trying to find an object's final velocity. Not really, but anything can be found in this. Equation number 1 is the final velocity will be equal to the initial velocity plus acceleration times delta t. Okay? Now, if you look at this equation, if you take a few moments to look at this, can you see where all of these different components appear in that stock equation above? Equation number 1 in UARM is nothing more than a rearranging of that stock acceleration equation. So this equation is a really short one, and it's a really good one to use if you're looking for acceleration, if you're looking for time, if you're looking for final velocity or even initial velocity. It's one of the shorter, or it just might be the shortest of the 4 equations. Okay? And when you use these equations, it's quite possible that you could have a word problem that will ask for about 3 different things, let's say. You would have to use one of the equations to solve for one, use that information to plug it into the next equation to solve for something else, and then use that information to plug into a final equation to solve for something else. Okay? So those are the styles of problems that you're going to get, and we will practice them. All right, so this is equation number 1 is pretty much one of the simplest equations that we've got. So we're going to move on to equation number 2. We know that when we have UARM, there is an acceleration. So in a velocity time graph, okay, velocity is a function of time, we know that the line is going to have a slope. All right, so the reason we get this equation, because this equation is looking at the area under the curve for this triangle, okay? Or even if, and I mean, that's not a triangle, but if I undo this and then I just draw it from, the origin, that's a triangle. So if I want to determine the area under the curve there, I'm going to go velocity times time divided by 2. That's where the 1/2 comes from here. Okay? And we see that it's velocity times time divided by 2. That's exactly what that equation is. That is an area under the curve equation. Do you guys see that? Do you see where this whole concept comes into play? That is that equation. Yeah? So if we're going to write this nice and neat, okay, we sit here and we go x final is equal to x initial plus 1/2 v initial plus v final times delta t. That is equation number 2. And it can be used to calculate displacement. The reason we would choose this equation over equation number 3 is that this equation is missing one of those variables. Which one is not in this equation? There's no a here. When we have equation number 3, right? The great thing about equation number 3 is it only deals with one velocity. And what's lovely about this equation is that if you're starting from rest and you're accelerating, you can cancel a lot of this. Final velocity is a non-issue in this equation, so because it's not in the equation. The reason we have no v final in this equation is because we substituted it out. So instead of having equation 2 here, where we've got xi plus 1/2 vi plus vf times delta t, we've actually subbed in for the VF here, okay, for this VF, we've subbed in this equation, right? This is where the acceleration comes from. So that, and the time squared. So that's why we end up having, okay, instead of having x final is equal to x initial plus, or sorry, 1/2 is multiplied by 1/2 VI plus VI plus AT, correct? That's,
Two VIs?
well, yeah, because look at this. This is what you're substituting in. So where you see the VF, you're replacing it by this. So what you're doing is you're actually getting rid of that VF. You're eliminating one variable here that you might not have by putting down something that you already have in the equation. Okay? So that's what gives us the actual quadratic. Okay. F-speak, whatever. So what ends up happening here is you end up getting this, okay? You end up with the actual equation above by substituting in, instead of that VF, by substituting in that additional VI plus A delta T, okay? This is a great equation to use when you're starting at rest and you don't know your final velocity. If you don't know VF, okay, you may have to use VF later on, and you know, you don't have your displacement, this will, if this is starting from rest, this whole chunk here ends up canceling out, right? So you gotta really read your problems carefully. You're gonna have to write down all your givens as well. We're gonna have a little recipe card, sort of, that we're going to use to follow when we answer these questions. Okay, there are certain things that you will be given marks for, which I expect to see. All right, so that's equation number 3 and how we get it. And let's finally talk about equation 4. Equation 4 is a nice one. It's nice and short. It's very similar to equation 1 in that we have VF squared is equal to VI squared plus 2A delta X. So this is another really great one if you want to find delta X or if you want to find one of your velocities. Okay? Notice how it doesn't have time in it. So this is obviously not one that you're going to choose if time is a factor. All right? You're going to have to choose, when playing around with these, you are going to have to choose equations that only are missing one variable. Because as soon as you have more than one variable missing, you start having to substitute things in, and that just, you saw what you said when we did the whole beginning, the whole subbing in here. You're like, what? I don't get that. So try to keep it as simple as possible, and you choose the equation that has all but one variable. Okay? You may have to go about a roundabout way to solve a problem, because you may have to get a variable that it's not asking you for, but that you need in order to solve the equation that you actually need.